are over 50 years old, and almost 75% of the building stock is energy insufficient. Considering the trend of growth in energy consumption and the fact that buildings are one of the key customers, the question of decreasing energy usage becomes a topical issue. And it's also important from the standpoint of planning, development, and construction of urban environments. As a strategic solution in 2002 was adopted the Energy Performance of Building Directive, which sets the framework for improving energy performance in European buildings, aiming to reduce energy consumption and CO2 emissions. This directive was revisited several times, introducing new standards and requirements for new and existing buildings. The later revision contained plans up to 2050. Implementing this strategy proposed in EPBD and in its revision has paid off. Household energy efficiency has improved by 29% at the European Union level between 2000 and 2019. Despite the increasing amount of buildings and appliances, the main driver of decreasing energy consumption is energy savings. At this scheme presents a systematic approach for single building retrofits, and specifically the part I want to put the attention on. The selection of retrofitting methods, which includes identifying the possible retrofitting approaches, estimate or predict the input of for each of identifying methods, validation, the applicability of and optimality of selected methods for the specific buildings with considering building characteristics, implementation costs, energy efficiency impacts, audit, and so on. The higher number of possible retrofitting measures we need to test for every single building, the more time and resources we will spend on this, and on a large scale, the complexity of this process increases significantly. Address a challenge here. Speaking about address a challenge, the building energy models that are used to simulate the energy performance and possible retrofitting methods are limited to methods that model can work with, and this leads to a very wide number of options to test without understanding the applicability of the specific buildings. And on the large scale, such approach leads to general recommendations that may not be applicable to the specific building, and the difficulties in developing and adapting these models. The challenge chosen for the project is to develop an approach to decrease possible retrofitting measures based on the building information and characteristics at the urban scale, and this way optimize the process of providing retrofitting recommendations for the building. This can mitigate the mentioned drawbacks and can reduce computation time and resources for energy simulation tools. During the background and related work research and analysis, the main founds that the most of studies select possible retrofitting measures for further validation as either supported by used building energy models or building simulation tools, or predefined at least based on some EPC or similar data specified for the specific country or the building site. Retrofitting method validations in most studies based on energy model evaluation result and not related to the testing the retrofitting methods as is. At an urban scale, this again leads to general recommendations and difficulties in adapting these models widely. After analysis of related work, the research gap was identified as follows. The step of selecting feasibility fitting options for the specific building or building stock is commonly skipped or does not include the analysis of the building stock. Often it is based on the computational and simulation model characteristics and possibilities. And was a research problem. Decreasing the number of possible retrofitting options will optimize the process, general process of choosing applicable measures, both for energy modeling approach or for human works for energy advisors. Because fewer input retrofitting options for validation means increasing the number of manually handled declarations or decreasing the computational time and costs for energy model and validation. And the research problem is defined as follows. Identifying and feasible retrofitting measures for the specific building based on already implemented or recommended retrofitting approaches for similar buildings in investigated building stock using the classification method. And the following research questions are formulated. Validate that the proposed classification approach is applicable for selecting potential retrofitting measures based on the building stock data. Identify the complete set of feasible retrofitting measures for specific building, specific buildings using multi-label classification methods. Identify a single retrofitting measure using binary classification methods for each measure in the whole set of possible measures. And validate the hypothesis that splitting data based on some natural criteria can enhance classification performance. For the classification task, we will use data in data of the Sweden building stock, specifically data from energy performance certificates, as it contains standardized building characteristics and information about implemented and recommended retrofitting measures. And to reach the goal, we will test different classification methods and their ensembles. Let's go to our data. The data was used in the research project provided by Swedish National Board of Housing. This data represented as an export from Energy Declarations data system, and it's not a format data set. Data contains information about buildings across Sweden. The data owner preliminarily excluded before export buildings without declarations and buildings with some unreasonable values, extremely small or large energy performance, and some large family houses. As most of real-world data, this one also has its own peculiarities. Data in Swedish, and firstly, all labels and categorical data had to be translated for further processing. As it's shown on the graph, new and implemented retrofitting measures are imbalanced between each other. Data contains different subclasses, for instance, single and two-family houses and multi-family dwellings. Data that belongs to these classes hardly can be mixed from retrofitting recommendation standpoints. So we will try to treat them independently as validation of our hypothesis. Since energy consumption depends on building characteristics, the data contains kind of natural outliers in energy consumption level, number of floors, building area, etc. First of all, we need to clean this raw data and form the data set for research. To start working with data, we had to clean them. And important features, let me emphasize the important features of the original data. Data split it into several files by year from 2019 to 2023. Single declaration may have several sets of retrofitting recommendations. Data contains several records for the same address, contain duplicated records, which may be as data adjustments as well as historical updates. Retrofitting measures were provided by humans, energy advisors, and were not additionally verified, so that the data may contains mistake in retrofitting recommendations. Retrofitting measures contains not standardized columns, kind of other recommendations for every group of retrofitting measures. And this information are not detailed and cannot be processed in classification tasks. We applied to form a research data set. We applied cleaning steps. We handled multiple recommendations, kind of merge them, because due to the nature of EPC data, it provided by a set of different recommendations for the same building, and to but all of them are applicable, so we need to kind of merge them to compile the whole set of applicable recommendations for a specific building. Uh, Several building with the same address was processed as following. We selected the main address because all of these buildings has kind of main address building, main address record, and that was chosen as a data point, and other was skipped. For historical updates, it can be caused by the updating data earlier than the schedule of kind of about 10 every 10 years it should be updated, but in some cases it may be updated earlier, or another case when data it's just corrections of mistakes in declarations. So we distinguish these cases by the date of declarations. And finally, we have about 2,300 declarations that was remarked as historical updates, real historical updates, and it's less than 1% of the total EPC declarations in the research dataset. They wouldn't provide significant difference, at our opinion, and may cause some kind of bias due to similar building characteristics. That's why we decided for this stage of research to exclude historical updates from this dataset. And as well, we provide general data cleaning, fixing correct values, number of floors that are physically nonsense, limit number of basement floors, and so on. Converting some text yes no fields to binary, one hot encoding, and so on. Excluded retrofitting measures, as I mentioned, that cannot be classified. Main characteristic of the Foreman data set for research. We got approximately 275,000 buildings and 110 columns. 28 columns contain retrofitting recommendations that will serve as our prediction labels. 28 columns contain implemented retrofitting measures, so we use as features, and 54 columns contain building characteristics and information about energy usage, and they also will serve as features. And data is imbalanced for every classification label, and between them, as we can see here on the graph, the biggest number of building with recommended retrofitting measure is not greater than 20% of total number of buildings, and total number of buildings with recommended retrofitting measure is not similar for every single retrofitting measure. Another important data characteristic is that most of numeric distributions are skewed and contain outliers. There are histograms of 6 features to demonstrate the skewed nature of the data. However, the data values represent real buildings and characteristics, and it's important in retrofitting decision making. So we decided to keep it. For experiment, we created 2 versions of the classification datasets. In these versions, columns that contains information about energy use processed differently. In the first version, in dataset 1, we save the detailed energy usage. The value of each energy usage columns is divided by building area. So we have energy usage per square meter by the specific source. And in the second version of the dataset, we mostly focus on total energy usage by type. So we summarize all columns that related to energy usage in 4 groups: total usage, heating, hot water, and electricity, and combined all other related columns to binary columns. And in both versions, we considered energy consumption values as energy consumption per square meter to mitigate the outliers in data as hard as we can. Let's go to the experiment settings. We plan to do two main group of experiments to test different classification approaches. Multi-label classification approach where we aim to predict the whole set of retrofitting measures for the specific building, and binary classification where each retrofitting measure recommendation was treated as a distinct label within the dataset. Let's start with multi-label classification and speak about the experiment settings. To validate our models, we employed standard training and testing procedure and split data in 80% for train and 20% for testing. To mitigate imbalance in classification labels, we used multi-label data stratification approach that implemented by in scikit-learn, scikit-multi-learn, scikit-multi-learn package. These techniques aim to ensure that the distribution of the number of targets in are similar in both the train and test sets. To evaluate the prediction results, we used F1 score average sample to again due to the imbalance nature of the data. And the following classification algorithms were chosen for our experiments, and for the multi-label classification, we choose three different approaches. It's general multi-label classification for methods that can work with this, and additionally multi-label classifier way. It's a strategy consists of fitting one classifier per target, and it can support kind of logistic regression for be applied to the multi-label classification task. And classifier chain approaches. This method takes into account possible correlations among labels and chaining them into specific order and training by the same classifier model sequentially on target labels. We evaluated 10 different features configuration and selected the ones that yielded the best performance for the classifier chain approach. Speaking about the result of prediction on whole data set, we gained the best value on complete set of labels is 0.42 obtained by a random forest classifier with classifier chain approach. The next experiment aim to validate the idea that splitting data in natural groups may improve classification results. First experiment is split dataset by year of building construction into three groups built before 1920, buildings that were constructed between 1920 and 2000 year, and buildings were constructed after 2000 year. The chosen splitting points are driven by the historical nuances of development of building technology and housing market in Sweden. Speaking about the results for this, best value for each subset achieved by a random forest classifier with classifier chain approach, and F1 score for weighted samples F1 score values for each groups is 0.34 for built before 1920, 0.44 buildings constructed between 1920 and 2000, and the highest score was obtained for buildings constructed after 2000 is 0.63. Across all methods, we have the clear trend that most recent construction period tends to better classification results, and it can be caused by the fact that buildings constructed before the 1920 has more individual characteristics and not that standardized, and that's why the results may be not good for classifications. The next experiment, we split building stock data based on the category to which the building belongs into three groups. It's multifamily dwellings, office buildings, and single or two family houses. The split is driven by differences in building characteristics between these categories. Speaking about the result-based value achieved by decision tree classifier and random forest classifier with classifier chain approach, except the multifamily dwellings and the forest with random chain was shows the best results, and for multifamily dwellings we see the best results shown by decision tree classifier. We can conclude that splitting data set based on building categories led to improved classification performance compared to using a complete undivided data set. And result of this and previous experiments supports the hypothesis that data segmentation based on natural criteria can show better classification performance. Usage of the classifier chain approach led to improve the classification results. The next class of the experiments is binary classification experiments. Here we have 28 possibility fitting measures, and in contrast to multi-label classification, we consider each measure as an independent binary label. For every fitting measure, we train separate classifiers on two dataset versions. Speaking about experiment settings, we again use the train split. It's the same train test split distribution, 80% and 20%. Due to handle the imbalance data, we use stratified technique implemented this sklearn package to ensure proper sampling of train sampling distribution of train and test data. And since the accuracy score not work well for the imbalance data, we stop our metrics as F1 score, precision, and recall. And the following classification algorithms was chosen for the analysis. Speaking about the result, we trained classified each version of dataset for every label and defined the best model for every retrofitting measures. The overall summary in a table concludes this result because it's hardly to explain for all of 28 measures separately. The best method are Ensemble's method, random forest, and XT classifier. They show the best performance for binary classification. And despite the high precision value, 0.93 in average, all methods show small enough recall, 0.37 on average, which also might be caused by the data imbalance nature. Based on the obtained result, we can conclude that positive validation for our research question about applicability of the binary classification. And additionally, considering values high precision and low recall, we can conclude that this binary classification approach, in simple words, can predict recommended retrofitting measures with high confidence but miss some actual positive cases. And taking this into account, we can conclude that this method can be used, for instance, to enrich building stock data sets where retrofitting measures are absent or incomplete.
1 minute left.
Okay. About the experiment implementation, we have more than 400 experiments in total for all versions of datasets and methods and classifiers. And that's why we limit to the selected approaches and stopped with default hyperparameters and did not apply the cross validations. And so it can be done in the following style of research. And again, given the data imbalance nature, it's harder to compare results between multi and single label classification. Conclusions and let's wrap it up. We confirmed that classification methods can be used to decrease the number of initial auto-fitting options in the Boolean innovation process. Multi-label classification methods is promising to continue investigation as well as binary classifications. But generally, obtained classification performance is not sufficient to consider it as ready to plan further utilization or industry usage. Low classification performance might be caused by the possible mistakes in data and imbalanced nature of the data. Overall, the results obtained in this research can be considered as a baseline for future work in this direction and future work and all matter. The several directions of future work. From data standpoint, it's validate data with industry experts to mitigate possible mistakes. In the ground truth test approaches to mitigate of data imbalance nature, for instance, test over and undersampling techniques. Enhance experiment design, use cross-validation techniques, hyperparameter tunings, and probably other more complex model architectures as was advised by my reviewer, and investigate the details of the best performing models to understand the nature of why we have such mistakes, and additionally validate the proposed research method on the other countries' data. And finally, I would like to thank everyone who has helped me and in this project, and specifically my supervisor, Alexey Pasichny, from the Kutykha Institute of Technology. And also, I'm grateful to RSAI for generously providing computational resources.
Thank you, Alexander. You are 3 minutes over time. So, anyone would like to start from the questions?
Okay, first question is, it seems like F1 measure is too low. F1 measure you obtain it is too low.
Yes, yes, I mentioned this, that the gained result is not sufficient.
Worse than random.
Why did you think so?
Hmm?
I'm not provided like continuation of random, and random is widely topic to discuss.
Okay.
Thank you for your talk. Uh, in your presentation, you said that you performed 400 experiments. It's quite a lot. Uh, Maybe you will share some tips how to process, how did you track all experiments, and like
Okay.
how to aggregate the results. You have like few tables and you have like 400 experiments.
Yeah, unfortunately, the presentation is limited to show all the results, and even the main thesis was shown the overall, and appendix contains more results information. And as an experiment, I consider the run of single classification method on specific data set version. So we split, like we created two versions of data set. First, we prepared the list of classifiers and developed kind of pipelines for running these experiments with different with parameters for both versions of dataset and the predefined list of classifiers.
It's not about this. My question. It's like you have results of experiment after you run the experiment.
Yeah.
And you will do something like, did you copy paste it manually into Excel, or
You mean
like
how I get
how you
raw log?
process all this data, 400 experiments results?
Yeah, you're near to the reality. It was generated log files for every single method dataset version, and depends on the nature of the experiment. Yeah, and then it was manually processed to kind of Excel for putting there in these tables and so on, because unfortunately Excel is still most convenient tool for
Okay,
table processing.
thank you. I have one more small one. So you had the results with different classical machine learning algorithms like random forest, neural network classifier. So uh, did you expect that random forest will be the top performer? And do you have any ideas on why it's so? Why random forest performs better than the rest with the huge margin?
Actually, no, there was no specific expectation about the model because it's quite a new task, let's say, yes, to classify the huge number of labels. And my inspiration why the random forest mm, showed the best result because it's quite mm, quite strict to handle the data imbalance and data mm, and different like kind of different values skewness in data, yeah. And yes, we can see on the slide it's mostly showed the best result on the dataset version 1, where we have more numerical data than binary labels, so we have like more numerical features to provide the decision. And the good point here is that classifier chain also boost the random forest classifier, so you can conclude that the order of feature uh, may be sufficiently significantly improves the results.
Okay.
Yeah.
And you didn't consider to try like light GBM or XGBoost, like gradient boosting over
Yeah, I
different
have this
ways?
question from my reviewers as well, and as I say, we was limited to the number of like to the time and computational resources.
Okay.
So we like decided to stop at some point to add more and more different classification methods. But it can be done in the future.
But regarding like random forest, did you explore a feature importance of?
No, as I
Okay.
mentioned again,
Okay.
the
Thank you.
diving into the details of decision making by the model can be did in the future. Can be done.
Alexander, can you answer your questions a bit shorter, please, because we are running out of time, and I think my colleagues want to ask as well. So it's to me, the major drawback of your work is that we didn't see the actual labels. You just mentioned recommendations that there are like R 28 or something different classes or whatever. But either in your presentation or at your thesis, there are no examples of data. You just show us headers without any examples, and we cannot feel actually what are the labels. Why is that?
Uh, okay, let me answer this way. So in Thesis, I have the list of all labels, and the encodings. It's in appendix. Uh, if I'm not mistaken, the very first table in the appendix A. It's encoded labels with English translated name of retrofitting measures. But you're right, neither in presentation nor in thesis, I didn't provide the examples like of real data in numbers. And
So, for instance, I'm looking at your appendix, and for instance, R1 code, blah blah blah, new radiator valves. So, either it for R1, so we have this column R1, correct? And so this is a recommendation, and it's either true or false.
Yeah, correct. It's this way. This recommendation provided in the energy declarations. It's kind of true or false.
So
Check
there are
the
like
box.
different 28 recommendations, and could it be the case when for one record there are multiple recommendations or only one?
Yes, yes, it's definitely the case.
Um. Okay, I see. I got it. And can you switch back the quick question, slide number 17, please?
17.
17.
Ah,
You mentioned you
okay.
feel no, no, yes, you feel empty values. How did you do this?
Depends on the nature. For instance, not all buildings have a solar energy system. So if we have no like energy input from the solar system, and in dataset it's marked as none, as just miss it, we marked it as 0. So it's no input kind of. For some values, okay.
Uh,
Thank you, Alexander. Could you please go back and go forward to your results and to the limitations of your work? Yeah, I'm curious about the last bullet, comparing experiment results and possible between multi and single label
Yeah,
classification.
let me explain in detail. So in multi-level classification, we have 28.
Concisely, please.
Okay, we have 28 classes and kind of at the same time, and we need to split in train and test to keep the distribution of each of this class in both train and test. So both train and test should have the similar distribution of features for every class. But in in binary classification, yeah, single level classification, we have only one of these measures, and we stratify. So we split the data to keep the distribution between like true or false values in this specific one, and it can be different and not applicable. Generally, it's not applicable for multi-class, because for multi-class you should coincide all at the same time.
Did you try to analyze any correlation between the multi-labeled and single-label classification?
To mitigate this,
In
no.
terms of statistical correlation?
Except of the no. Let's say
That
this.
could be
Not
interesting.
not
Could be interesting to see, by
Yeah.
the way.
Thank you, Alexander. I have a short question which actually evolves from the previous ones. There are 28 recommendation measures, but some of them are definitely related. For instance, I see in your thesis something to, installation of solar cells and installation of solar heating. Of course, the second is not possible without the first one. So did you try to find any correlation between these recommendation measures and respectively to single out the variables which contribute the most to the blocks, to the clusters of these measures?
Let's answer this way. So we like not split them additionally into groups, because they are also divided into groups by the nature of energy performance declarations. So for instance, all solar system measures will be grouped into one, like listed together. The second point here is that we have implemented implemented retrofit measures and recommended retrofit measures. Implemented we consider as a feature, and recommended as labels. So we, in this case, for example, just like as an example, we can have the first one as implemented, for example, solar system for energy, but solar system for heating may be advised to implement. That's why we not consider combining them kind of together, removing something and so on. No, this approach for clustering was not considered, but the relation between them was considered by testing the classifier chain approach, which definitely shows the best result. And this specific method combines, shows the result dependent on the order of the feature measures.
Thank you, Alexander, for the presentation. A couple of quick questions. So what is the output of your classifier, multi-label classifier? What is the size of your output vector?
It's 20 for multi-labels. It's 28. It depends on the number of labels.
No, let's assume you have 25 classes. What is your output? 25 options. What is your output of your model? What is the size of the output vector?
25. It's the same.
Okay. And I'm curious because you have like multi-labels, so you can for one vector option, you may have multiple classes. How?
Not exactly. It's multi-label, but binary. So we don't have multiple classes. We have only 2 classes for every single label. It's kind of different because multi-classes approach can be when we try to predict, for example, 3 colors.
Okay, I see.
Yeah,
I
but
see.
here we have only binary
My
classification.
next question was I didn't saw in your presentation as your work any maybe confusion matrix. Have you tried to visualize it to see what for what classes classification works good, for what classes works bad?
No, no visualizations. It's table listed results.
Because you provide aggregated metric, it's very hard to understand what work for what classes it works good, for what labels it
You
works
mean
good.
for binary classification?
I mean for classification in general. How do you know? For example, you have option A. You recommend you. How can you understand if your classifier doesn't work for that option? If you have
I'm a bit
only
confused
aggregated
because
metrics.
I provided the different representations for multi-label and binary label classification. For multi-label, we present the whole set and evaluate the performance prediction on the whole set, kind of on the whole vector, yeah. And it's just a score result. But for binary classification, when we evaluate every single feature measure separately, we listed in I listed in appendix results for every classes.
You said that your output vector is 25, right? Size.
Okay.
So you output 25 numbers. And for some options, it may work okay. For some option, it may not work. And if you visualize it, you can understand, you can check what is the true positive, what is false positive for your particular class. When you aggregate all metrics, you lose this information.
Yes, for multi-label classification, we did not do this analysis, and it can be considered in the future one.
Okay, but for binary, it also counts as far as I understand.
For binary, it's like it's comes from the nature of experiments because we take this every single
okay, so you train a separate model per separate class.
Yeah, correct. It's the nature of the experiment.
And really briefly, what is the Hamming loss?
Hamming loss, it's kind of a metric to determine how many, like in simple words, how many targets was predicted negative, false, no, mistake, just kind of mistake, mistakes. Understand?
Okay, thank you. I think we don't have any questions. Thank you, Alexander. So we are moving on, and so the next student is Antonino Volkotrup, and she will be presenting and then defending her thesis entitled Using Beneficial Ownership Data for Risk Assessment in Public Procurement. And she was advised by Dr. Mihaly Pazakas. Please.
Hello, everyone. Thank you for having me here. And yes, today we're going to talk about public procurement, risk assessment in public procurement with usage beneficial ownership data. Yes, and our plan, we start with topic importance, move to related works, talking a little bit about problem statement, and then we start talking about solution. Data, modeling, results, and our future steps in this research. Why this topic is really important, that we see increasing trends in public procurement spending, and the more money we have, the more risk we also have, especially money laundering risk or risk to receive overpriced goods and services and some unfair competition. Actually, we have a lot of investigations which provided about unfair money spending or examples of unfair competition. But before we move further, let's understand who beneficial owner is, because then we will talk a lot about beneficial ownership data. And beneficial owner is a person, not a legal entity, but person who really owns and receive benefits from the company activity. So, for example, if Renat Akhmetov owns Ukrainian company through offshore company, his name should be mentioned in beneficial ownership register. And these registers were opened from 2015, and Ukraine was the first country who opened this register. So let's move to related work. Luckily, we have a lot of usage machine learning algorithm in anti-corruption and in procurement cases. The most prominent examples usage of machine learning in anti-corruption is case in Brazil, when it was used for prediction the corrupt behavior of the state officials. However, these algorithms were very heavily criticized. It was caused because people who create this algorithm, they didn't show the data on which this algorithm was trained, and it was not evident how it works and how it predict this behavior. The second case, it was classification, local municipality, whether it was corrupt or not corrupt. So here it was used classification algorithm. In machine learning in public procurement was heavily used by Dozora teams. It's our Ukrainian team, so it's very close to us. They try to identify risky tenders, but they use heavily the data which were available through public procurement data sets. And there like another research team who also worked with public procurement data, they used a classification algorithm, tried to understand which tenders were corrupt, which not corrupt, but they analyzed tender documentation and exact some specific words, so they used like NLP for their research. Unfortunately, there are not many actually not published yet results of using machine learning with beneficial ownership data. Right now, a lot open ownership team provides a lot of research with beneficial ownership, and one of the example is correlation between beneficial ownership transparency reforms and domestic policy goals. But in this case, they used linear regression, and the results were not very satisfying when actually bio transparency doesn't match with domestic policy goals. So they start to using like mostly non-linear regressions. So our task is to use beneficial ownership data in order to identify risk indicators for each person who owns companies and for companies. And in order to see that if this company win a tender, this tender may have some risk, some corruption risks. And we need to analyze this tender deeply. In our solution, we firstly go to data, modeling, evaluations, and results. And let's jump to data. This is, to be honest, like data in this process is the most difficult. The first case, public procurement. Public procurement data were collected from two different sources. For EU countries, it was like Denmark and the UK, it was from Open Tender, and for Ukraine, it's from Prozoro. And it's very heavily, it contains like mostly 90 variables, but for us, the most important are control variables, which have like influence on our dependent variable, but are not in the interest of our analysis. They will be tender year, tender price, buyer tab. We need to know whether it's state or local, and CPV codes. We need to understand what type of product or services were bought. And the most interesting part is our dependent variable, our label. It's generated and it's average of sub-indices. 3 of these sub-indices are connected with time. It's like call for tender publication, length for submission, and length for decision period. But and the second 3 are the most important because a single bidder contract it's like when we have a case, if we have competitive market, but we have one bidder, it's quite strange, to be honest. The second one is procedure type. When we have negotiations, so we know that we will have one bidder and we just negotiate. We don't have any transparent procedure. And buyer dependence. It's a continuous variable. When we calculate in what percentage of tenders were won by one bidder. So why do we need CRI? And why can we use like single bidding contracts in case of classification task? Even when we have like we have one bidder, yes, it's risky, but we cannot say that 100% this procurement is risky. We need something average, and we need something which provide like regression task and provide some percentage of riskiness according to which we can say, okay, this tender can be risky. And CRI indices vary from 0 to 1. And bioregisters. We have 3 different bioregisters, and unfortunately, in contrast to procurement data, bioregister data structure is completely different, and every country provides the information. And for example, Ukraine doesn't provide information about beneficial ownership, beneficial owner date of birth, and company registration in machine learning format, machine readable format. Unfortunately, this access was closed in 2022 because of Russo-Ukrainian war, but we worked just to open it. The next register was the UK register, and it was really interesting that they don't have company names, and you have to use one more source of data to extract them. And then Denmark register, it was the eldest one, but the most full one, honestly. Yeah, that's why, because we have so different data structures, in modeling we cannot use like, we have to use modeling to 3 different countries and to build like it separately, not unify the data set. But before building modeling, we have to match beneficial ownership data with public procurement data. Here we have 3 steps. The first steps, we have to match like through company IDs. Actually, Ukraine has the highest percentage of matching, and this caused because Ukrainian companies, all Ukrainian companies have tax IDs. In contrast, UK procurement data sets have only just cover this only 15%. And here we have moved to matching by company names, and it's the most inaccurate and the most dangerous option, because in company names we may have like in France the case when several companies can have the same name and you cannot match them through the names. Or at least like we saw in the UK cases when some company names have spelling mistakes in procurement data and in registered data. And the last step of matching, it was using with a period. Denmark and the UK data provide historical data of beneficial owners, so we can cover all procurements like in historical perspective. Unfortunately, Ukraine doesn't have this information, so we cannot do this for Ukraine. And as a result of matching and and result of usage all our data, we, in order to build some models, we create some features. This is our risk factors for beneficial ownership data, and only one we have for companies. It's company maturity, like the date of registration of the company before winning the tender. Unfortunately, only five variables are available for all countries. But some unique cases like BioPAP, which are available only for Ukraine, because politically exposed person data set work only in Ukraine. So when we have our data mesh, when we have our feature created, we have to work with models. We have linear regression just for comparison. We have group of ensemble modelings like random forest, decision tree, and gradient boosting, and we have canine regression. The biggest challenge of all nonlinear regressions, it will be explainability, and we will talk later why. But all of them is expected to receive high accuracy of prediction. However, in some cases it doesn't work because some models are dependent from hyperparameters tuning and selections. So here, like if you do something in the wrong way, you don't receive really good results. And evaluations will be with three factors. The first one, coefficient of determination. Second one, mean squared error. Is just for model comparison. And later I explain why we need our max error. The first, so let's see the results. We built two groups of models. The first one was without control variables. So we use only labeled labels from procurement data, CRI, and use all our biofactors and build a model. And we have really poor results with accuracy. And this was caused because of the fact that one company can win simultaneously risky and unrisky tenders. So, and the model's like, okay, what type of results should I choose? We need to help somehow for modeling, and that's why we added control variables. Because it's impossible to have the same tender price, the same CRI, the same buyer, and the same tender year, and the same product. That's why the results improved significantly. In alternative solution of usage control variables, we can do some CRI aggregation, just to have that one company have one CRI index, one label. But in this case, we lose a lot of valuable insights, or alternatively, we have to do very difficult aggregations with usage all these control variables in an aggregation stage. So here we decided to stay with controls, and we can see that random forest provides the best results for all models with our controls, and that's why we will move with random forest further. Here, the third our evaluation matrix was maximum error. So it's like a difference between predicted and real value. So what we have that especially is the most problem for the biggest problematic for Ukraine, because unrisky procurement can be predicted as risky. And unfortunately, in this case, we cannot use these models because it's very dangerous when you fire a supplier named and labeled as unfair, because it can be used by its competitors. For us, it's like a maximum error should not be higher than 0.5. So when you unrisky procurements, they stay unrisky even in case of the worst prediction. Denmark almost is very close to that, but still it's higher than it was. The second result, what we see, it's our feature importance. Definitely the most important, and we saw on the previous results, are a group of our control variables. However, very interesting insight what we received there, that CPV codes are very different for every country. And for Ukraine, it was road construction. And definitely, after having Zelensky program with big construction, it's one of the most important CPV code. But what we will have if we change our construction to the military CPV codes? Here is the questions to random forest. The second, what we notice that in our feature importance, non-dummy biorisk factors are on the list of importance. However, random forest ignores all low-frequency dummies. It mentions that, okay, it's not important for our results, and that's why we name them as unimportant. And the third questions what we have with random forest is interpretability. When we have linear modeling, we say, okay, our coefficients is 0.5, and if we have some increase in one for our risk factors, we will have such influence on our CRI index. We cannot say the same with random forest. We cannot say that if we have bio frequency 41 and everything what we hire, if our bio frequency higher than 41, it's number of company owns by one bio, then it's risky. We should analyze everything in exact case with exact set of features. However, if we can build a random forest tree and understand the logic, one tree or out of random forest, understand the logic how this decision was made, and we also can use Shapley additive explanator, which it's graph which can provide like detailed influence of each variable to our result of our dependent variable. So, however, in conclusion, what we have, first of all linear models overperform our linear regression. And random forest in this case was the best. But what we have that low frequency dummy variables have really low importance. And for me as an analyst and domain expert here, I'm very sad because these dummy variables are very significant for us from analytical perspective. Because if we have someone who live in Jersey, and this person who live in Jersey, which offshore residence, have 60 companies, it's something strange when this beneficial owner mentioned as a real owner in the UK register. So it's like my personal red flag, but unfortunately it doesn't work with random forest. And the third moment what we have is random forest, that trend dependencies. That's why we assume that a result for Denmark were the best for random forest and other modeling, because Denmark is very stable and they have like long-term trends without this jumping with governmental changes. And building such models provide better results for developed countries in contrast of developing, or in contrast to countries who have this really changed some trends, and these trends can be changed very, very quickly. Here we have the next future steps. As we said that we depends a lot from the data. That's why we have two type of tasks. The first one is advocacy steps. We need to advocate open data, and we need to advocate high quality data. For instance, in Ukrainian beneficial ownership register, from manual access, you can see date of birth of each BO. But still, we need to have the data in machine readable format. So, but it requires some advocacy campaign. We need to advocate that more registers should be open in different countries, also in machine readable format. And if we say about beneficial owners, like a person, okay, I can hide behind different passports, for instance, and how a machine machine should identify me as Ukrainian and me as a person who owns Cyprus passport. Or let's say the third variant, me as Israeli, when I change not only my nationality, but also my name. And here we need to find something unique for all countries. And final for machine learning usage, right now we're working with more 4 countries. It's Latvia, Slovakia, Estonia, and France. And we will do additional research and I hope we will publish the results connected with these countries. And this is analysis for public procurement data. And then we were thinking about creation a nominal owner prediction model. This model doesn't relate to public procurement, but relate to beneficial owners risk indicators, which can be tested on public procurement data. It can this work and some insights of this work can be start of this second model. So here I'm done. Thank you for your attention and be happy to answer to all your questions.
Thank you for a nice presentation. I have a quick question. Michael, go to slide number 20. 20, 20. I'm a little bit puzzled by the names of the extension countries here. It looks like Latvia and Estonia are positives in terms of having their digital infrastructures and the information you would like to collect. Slovakia is still okay. France is also very developed with smooth trends as far as I believe. Why not Italy? Mm. 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 So you have stolen my next question. Why not Cyprus? Okay. Uh, 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 right. All right. Why Europe only? Why only Europe? Okay.
Thank you, Antonina. Very interesting. But can we get back to the very beginning and can you repeat how you merge those data sets? So we have public procurement data set and beneficial ownership. Like a company. Yeah, so sorry to interrupt. So I mean that the core data is procurement data, and then you enrich it with the beneficial ownership, so to bring those beneficials to the procurement data. Okay, and then the main task for you is to actually predict those misbehavior or corrupt and find those beneficial owners, right? Okay, then I got it. And what is the size of the data sets? It's because of Prozoro. Okay. Is it for because of the size or because of interpretability? Mhm. But have you tried to use ANNs for Ukraine? I see. Okay, got it. And the last one from my side. So I assume that the whole work treating with this data is quite time consuming. So what was the most time consuming part of your work? I mean not country, but in this pipeline. Yes. So in terms of pipeline, like data merging, data pre-processing, running experiments, in terms of working in not your like we know that you work in this sector, but in terms of the master thesis work.
Uh, the question is, you mostly speak about models and general average scores, but what is about specific examples? For example, you mentioned something with road construction program and this. Can you give us specific examples of this procurement corruption risks?
Okay, but it's still about good, but it's still about um, parameters and features and so on. I'm speaking about very particular tenders, very specific examples of, okay, we have this, yes, exactly. So to make a like ranged list of top first with the most corruption risk, the second one with this, why? Understand, clearly understand, but try understand me. My point that you analyzing corruption risk in indicator, so you can calculate it. So why don't you provide this list by the absolutely specific database from Ukraine, for example?
I also have a couple of questions. Thank you for your presentation. So do I understand correctly that actually you do a classification and you predict a final regression? Okay, regression, and is output of your model is the probabilities that or what? Mhm. Okay, so okay, got it. Thank you. Then you also mentioned that you discard some columns, some data that are present, for example, in Ukrainian dataset, but are not present in other datasets, right? Please be concise. Okay, so you include all the columns, and if one register doesn't have that values, you put just none or something like that, right? Okay, and have you performed some failed cases analysis, the worst cases that have a performance and why they have bad performance? But per country, right? But and also I'm curious, so these registers, they have multiple rows per beneficial owner, right? Do you treat them like as independent rows, or do you also count for some dependency between these tenders? So you mark the same BO owner multiple times, right? But does the person, for example, if I won the good standard, I'm good person, I'm not risky, but if why I'm not marked like risky person in all the history if I was noticed that. Okay, okay, I see. Okay, okay, I see. Okay, and my final question, so as far as I understand, these models have to be kind of continuously updated. For example, you may have some model and when I get new data, I have to update it. Do you have some ideas on how to do continuous integration, continuous deployment? Okay, okay, thank you.
Yeah, okay. Quick question about your evaluation in terms of maximum absolute error. Have you considered analyzing kind of false positives or false negatives? Yeah, it's regression, but you anyway can fit this concept here. Yeah, have you tried this analysis? Yeah, okay, that makes sense. Okay.
Yeah, just quick one at the last moment. So when you came to our program in 2020, I remember during your interviews that you emphasize that you want to use all this data science stuff to work with this problem. So in terms of on scale from 0 to 10, are you satisfied? Not about program, but the result. From 0 to 10, then you know one number. Okay, thank you so much.